My name is Dr. Helen Lever, and I have prepared this tutorial to help students with the definitions of the various parts of sequences and some recognition criteria to help in exercises about sequence stratigraphy. What I'm going to cover here is a summary of the original sequence stratigraphy model as published in 1977 by Vail et al. This model has been discussed and modified extensively, and new subdivisions of sequences, alternative models, and nuances of meaning are everywhere in the literature. However, it is, I find, usually best to start with the simplest model and then work up to the variations that may or may not occur in your own experience. We will look first at the various definitions and then at the recognition criteria for the various subdivisions of sequences, and finally I want to end with a short discussion on how to create chronostratigraphic diagrams. Before we start talking about the sequences themselves, we need to make sure that everyone is aware of some of the terminology that we will be using to refer to stratal relationships. The most important terms are those related to the termination of strata against other strata. These diagrams are based on the seismic images in which these relationships were first observed. The lines here then represent reflectors that are clearly identifiable on the seismic line. In order to define sequences in these seismic lines, termination patterns at the top and the base of the packages are used. The top may be truncated by erosion or may lap out in a top-lap relationship caused by progradation in high stand conditions. The base may lap out by on-lap, which is gradually rising layers caused by sea level rise in high stand, or down-lap, layers truncate onto a surface and build outwards during progradation. In this diagram, also based on a seismic image, we see the full relationship of these strata within a single sequence. We have on-lap, top-lap and down-lap occurring during different parts of the sea level rise and fall that is creating the sequence. So you can see here how we can use the different relationships to define subdivisions within the sequence itself. So a sequence then is a stratigraphic unit composed of a relatively conformable succession of genetically related strata and bounded at its top and base by unconformities or their correlative conformities. This is based on the concept derived from the stratal relationships that we've just defined based in seismic lines. This is the definition from the original paper on the subject. Note that here the genetic relationship that is assumed is the sequence is deposited during one episode of sea level rise and sea level fall, and also note that the boundaries of the sequence are defined as not merely being the unconformities, which are created on the shelf by the exposure during sea level low stand, but also the correlative surfaces in the basin area where sedimentation was continuous, and therefore there are no unconformities present. The boundaries in the basin area are assumed to be the lowest sea level surface, which may be extremely difficult to actually recognise reliably. However, this is the date that is given to the boundary of the sequence. Often when only shelf sediments are studied, this time must be estimated based on the age of the eroded high stand and the deposited low stand, i.e. the range of time that is missing across the unconformity. Note that also that the sea level change assumed in their original paper, largely based on successions from passive margins, was eustatic or global sea level change. However, in many shelf regions, there is a significant effect from tectonic activity, which is capable of producing relative sea level changes. And a relative sea level change is just as capable of producing sequences as a eustatic change. Indeed, there is a lot of current activity in the research world into attempting to identify the differences between sequences which are controlled entirely by tectonic effects and those produced entirely by eustatic sea level changes. One way, of course, of differentiating is in correlation and dating. Those sequences created by eustatic changes should be correlatable between basins because the same eustatic change is occurring everywhere worldwide, while those created by tectonic events should be limited to the immediate area or basin that the sequence is occurring in. However, with active basins, eustatic signals are often overprinted by tectonic signals, and it is difficult to identify exactly which sequences match those already identified elsewhere. Sequences, so these are these genetically related units bounded by unconformities and deposited during a single cycle of sea level rise and fall, are subdivided into sections called systems tracts, which are defined based on which part of the sea level cycle they were deposited in. For example, during low sea level, we have a systems tract called a low stand systems tract. A further subdivision of systems tracts is possible with what are known as parasequences. and parasequences are often linked to the reflectors observed within the system's tracks themselves, that is, they contain or are bounded by sharp lithological contrasts. Parasequences tend to be little coarsening upward successions, and their boundaries are flooding surfaces, that is, abruptly finer units, as opposed to the sequences themselves, where the bounding surfaces are sea level lows. This, therefore, is the whole sequence from sequence boundary to sequence boundary, and it contains the 3 systems tracks and many, many parasequences. This style of drawing that you can see is meant to imitate a seismic image, with the lines representing reflectors that are probably the top surfaces of parasequences, these flooding surfaces, parasequence boundaries. Parasequences then occur between 2 reflectors, 2 flooding surfaces, and a small coarsening upwards successions topped by flooding surfaces. They will, of course, contain a number of beds of different lithologies, just to make the terminology clear. Parasequences are packages of sediment separated by flooding surfaces. These represent minor fluctuations in sea level, or possibly just episodes of progradation caused by fluctuations in sediment supply or other factors. The pattern of parasequences is vital to the understanding of the overall trend in sea level that creates sequences. They are stacked vertically, as in this example, or they might be overall prograding or overall retrograding, and you just need to be aware of the difference in scales at which we're going to discuss this, prograding and retrograding activities. All parasequences are prograding, but they may form part of an overall sequence that is retrograding or prograding, depending on what the sea level is doing during deposition. Systems tracks are parts of the total sequence that correspond to various parts of the sea level changes, low, rising, high, falling, for instance. They are separated by various surfaces which represent events or phases of sea level rise and fall. A low stand systems tract forms after the fall in sea level and during the period when it is low to slightly rising. A variety called a shelf margin systems tract occurs when the sea level fall is relatively small, so that the new sea level is not below the level of the shelf. Low stand systems tracts sit on top of the sequence boundary or correlative conformity and are overlain by a transgressive surface, or sometimes an erosive surface called a transgressive surface of erosion. A transgressive systems tract forms after the rate of sea level rise exceeds the rate of deposition, at which point the shoreline begins to retreat landwards, retrogradation. Transgressive systems tracts are often condensed with low rates of deposition, since deposition is concentrated on the shelf and is not being transported basinwards due to the rapid rate of shoreline migration landwards. Common indications may be to see an increase in glauconite concentrations, carbonate content, and biotubation throughout the transgressive systems tract. A TST sits on the transgressive surface and is overlain by the maximum flooding surface, which represents the maximum landward migration off the shoreline. A high stand systems tract forms when the rate of sea level rise slows and the rate of deposition begins to exceed it, so that the shoreline begins to move basinwards and the sediment stack begins to prograde. Therefore, there is an increased downslope transport into the basin as the shoreline begins to approach, and increased sedimentation rates there as well. You get less glauconite and carbonate being deposited. This is then overlain by the erosion surface created during the next sea level fall, which is the sequence boundary. This set of systems tracts represents the originally defined set created in 1977. However, many geologists looking at their own data saw a need to define other systems tracts to take into account the stratal arrangements that they were seeing. For instance, many recognised the need for a regressive systems tract to take into account 6 successions of regressive strata that did not correspond exactly to high stand systems tracts. Others wanted to define specific tracts that matched their observations. For instance, some successions routinely developed a condensed section at a specific place in the sea level cycle, so that these geologists wanted to define a condensed section systems tract. And there are lots of others that could be given as examples, but the best way to find out about these is to read papers on the subject, which then illustrate the theory with their own examples. On to talking about sequence boundaries, which are a surface separating younger from older strata along which there is evidence of subaerial erosion, truncation, or submarine truncation or exposure, with a significant hiatus indicated. As we have discussed before, there is a difference in architecture depending on the magnitude of the sea level fall, and especially whether the sea level fall goes below the shelf breakpoint. If it does, as in the case of a Type 1 sequence boundary, when we have a high rate of sea level fall, we get a marked change in the shoreline position, an abrupt shift to shoreline and facies basinwards. This results in subaerial exposure of the shelf with erosion, incision, and downslope transport of sediments into low stand fans and wedges. If, however, the sea level fall is not fast or not a great amount, then the shelf may not be exposed, although submarine erosion may take place due to the shallow water conditions. The shoreline may remain in one place or may move basinwards, and there will be little or no onlap since there is little accommodation space being created for sediments. The variety of low stand systems tract that develops then is called the shelf margin systems tract and has a different architectural appearance from the low stand systems tract. Having defined the individual systems tracts, let us look now at how this works when building up a sequence and some recognition criteria other than those already covered. We start with a little prograding set deposited during high stand. The sea level drops, but not enough to expose all the shelf. The new set of strata has onlap onto the previous high stand deposits or may top lap out against the limit of accommodation, which is going to be sea level. Low stands are progradational, so the downlap points move basinwards. There is no incision, although there may be marine erosion. There is exposure of the most landward parts and an unconformity is developed, and this is the type of low stand which is called a shelf margin systems tract. After the rate of sea level rise exceeds the rate of deposition, the shoreline begins to step back landwards, which is called retrogradation. Note that the downlap points step rapidly back landwards as well. This is a key recognition criteria for the transgressive systems tract. The point of change is called the transgressive surface, and there are many cases where it is erosive due to the change in dynamics caused by the rising sea level. Transgressive systems tracts are characterized by condensation, increased organic activity, current activity, and carbonate content. The onlap points migrate landwards until they overtake the previous high stand onlap locations. The maximum flooding surface at the top of the transgressive systems tract is the maximum landward point of marine migration and is represented by the last flooding surface parasequence boundary, where retrogradation is occurring before progradation begins in the high stand systems tract. You can see that with the high stand, the downlap points again are migrating basinwards, while the onlap is continuing to rise and move landwards, although more slowly than before. High stand systems tracts are associated with the highest sea level and also the beginning of the fall in sea level. A Type 1 sequence boundary where the sea level fall goes below the shelf break results in incision and erosion on the shelf, with the redeposition and rapid transport of material downslope onto low stand fans. Low stand deposits are progradational, but much shifted basinwards in location, and the onlap of their strata occurs against the layers of the previously deposited high stand. We can continue to develop further systems tracts, but we can now summarise what we should be seeing. High stands tend to be aggradational to progradational, while transgressive systems tracts are retrogradational, and low stands are again aggradational to progradational. Look for incisions, top lap relationships indicating lack of accommodation space, which is very common in shelf margin systems tracts, and the pattern of shifting downlap and onlap relationships. Here is a good place to discuss why further authors decided that there needed to be defined a forced regressive systems tract. If you look at the normal regressive situation at the top, you can see that this is like a high stand where layers are continuing to build on top of each other as well as prograding basinwards. However, in the second diagram, you can see that when sea level is falling, there is no space for accumulation on top of previous layers. So the deposits actually step basinwards as they are deposited during the sea level fall. This may manifest as top lap or as actual downstepping, depending on the relationship between the sea level fall and the sediment supply rates. In order to conclude this architecture in sequences, authors created the extra systems tract, a forced regressive systems tract. Now that we have been through the sequence model, we can think a little bit more about where the sediment is going through all these changes in sea level. For example, in the basin regions, sedimentation is at a maximum during low stand, when erosion is taking place on the shelf and incised valleys are concentrating sediment transport and delivering that sediment to the basin areas directly. This is the time when thick deposits of turbidites or even shallow marine deposits may occur in basinal areas, something to be aware of when searching for reservoirs in a basin under exploration. During transgression and high stand, accommodation space is created on the shelf area and sediment supply to the basin may be completely or partially shut off, creating unconformities due to sediment starvation or condensed sections, hence the development of special subdivisions like the condensed systems tract. On the shelf, obviously, sedimentation is at a maximum during transgression and high stand, and erosion will be taking place during low stand. The actual geometry of the sequence is controlled by the balance between the accommodation space and the supply of the sediment, as well as factors like tidal range, storm strength, original shelf shape, current activity, and of course local tectonics. These factors of course may change along the strike, so that sequences may appear different in shape depending on where in the margin they have been deposited, despite being created by the same variations in sea level. Now we will look at the kind of exercise that may be used to determine that our students understand the definitions of sequences and systems tracts. This diagram uses the same convention that others in this presentation use, that is that this is like an interpretation of a seismic line, and the lines drawn represent reflectors or parasequence boundaries, those flooding surfaces. What I suggest is that you pause this and see if you can identify the sequence boundaries, low stands, transgressive and high stand systems tracts, transgressive surfaces and maximum flooding surfaces. You may need coloured pencils. Ready for a discussion? Okay, so what we are looking at is the stratal patterns that we have gone through already. Let's start with looking for the sequence boundaries. Look for incision and a basinward shift in the onlap locations. For example, you can see that between reflectors 18 and 19, the onlap location shifts basinwards dramatically. There is also clearly incision on the surface 18, so this is our sequence boundary. The strata overlying the sequence boundary will clearly be the low stand systems tracts, and then there will be a point where the downlap stops moving basinwards and starts moving landward. The clearest example here is between reflector 31 and 32. 31 shifts basinwards in its downlap location, while 32 and 33 clearly shift landwards. This brings us to the point where the maximum landward sea migration occurs, which is actually probably above 33 and off the picture, but can be defined as the surface 33 for the purposes of this example. Then we have progradation and more basinward shift of our downlaps for the high stand systems tract, and we are back on to the start of the next sequence. Here the surfaces are coloured to help illustrate where all the systems tracts start and finish, so that you can see them more clearly. A final part of this kind of exercise of identifying systems tracts is often to translate our diagram into time. This is called creating a chronostratigraphic diagram. The drawings we have been looking at are our depth-distance diagrams, although being based on seismic images, the depth scale is somewhat exaggerated. But it is often very useful to convert our thinking into time-distance relationships, so that we can actually study when things were being deposited where. In this way, it is easy to identify unconformities and correlative conformities, as well as condensed sections and non-deposition. In this small example, you can see what the extent of each layer in the depth distance diagram at the top has been simply transposed directly onto the appropriate line on our time distance diagram. We can do this so long as we assume that the flooding surfaces or parasequence boundaries are in fact time significant. Theoretically, of course, they should be. This gives us the diagram in time, which as you can see highlights the unconformity and non-deposition that is part of the building of the sequence. We start building one by creating a diagram like this, where all our reflectors are given a straight line representing the same time in the time distance diagram. We then need to translate our distance information from our depth distance diagram onto this. So place one diagram above the other and transfer the information vertically with a ruler. Have a go at this first, and then continue with this presentation. Ready? Okay. Here is a very basic rendition of our complicated stratigraphic diagram into a complicated time diagram. I've included the colours for sequence boundaries and other surfaces to help keep track. If doing this properly, we can make it look much more realistic by showing the edges as little progradational pulses and by thinking about where the facies would be. For example, this pair of depth distance and time distance diagrams have annotations showing what kind of reflector termination is occurring on lap versus down lap, and also colours to help identify the different facies being deposited. Think how useful that will be in determining the likely location of reservoirs and seals. From this chart, you can also derive a sea level chart, showing the relative size, shape and timing of the changes in sea level through the development of these sequences. This tutorial has covered the original sequence stratigraphic theory, including criteria for identifying the different systems tracks and surfaces in seismic images and pseudo-seismic line drawings. Practice this yourself to make sure that you've got the theory properly learned and can move on to learning about more complicated models and sets of systems tracks. Think about where are the different facies being deposited and where might you look for stratigraphic traps. Look for further information in our slide packs for topic A or for websites or papers or books on the subject, and enjoy.